Alright then, carrying on with vectors. So we're going to be looking at the vector equation of a line. And I thought I'd start in two dimensions. Now this is important because when we're dealing with the equation of a line in 3 dimensions, if you want it in Cartesian form, it's an equation with 2 equal signs. And it's not particularly friendly to work with. There. So we don't tend to represent the equation of a line in 3D space in Cartesian form. We tend to write it in vector form. So I thought I'd introduce this concept by looking at a 2-dimensional example, and then we can extend that to 3D. Okay, you happy with that? Awesome. Okay, now the idea of finding the vector equation of a line is you have 2 vectors. One vector will take you from the origin to any point on the line. Okay, I'm going to call it A. And then the other vector is any vector in the direction of the line. Okay, so you have one vector to take us from the origin to any point on the line, and then we have another vector which takes us in the direction of the line, and that can be any vector in the direction. Okay. So I've got here the equation of a line is y equals a half x plus 2. So I'm going to say this is the point 2, 3, but it could literally be any point on the line. Okay. I'm going to refer to this as vector A, and that as vector B. Okay. So, what's my vector A? Well, that's going to take us from the origin to the point A. So I've moved 2 in my x direction and 3 in my y direction. So the vector therefore is 2, 3. The vector B is any vector in the direction of the line. Now this line has a gradient of a half, which essentially means every time I go up 1 in the x direction, I go up half in the y. So I could have the vector 1 and a half, but it can be any vector in the direction of the line. So let's avoid the fractions. So instead of going 1 in the x and half in the y, I'm going to go 2 in the x and 1 in the y. Okay, that's the same gradient. So 2 in the x and 1 in the y gives us the vector B. And now that we've got the vectors A and B, we take those 2 vectors and we sub them into this equation here, which is the vector equation of the line. xy equals A plus lambda B. So in this case, we would have xy is equal to 2, 3, excuse me, plus lambda times 2, 1. So what this vector does, it will take us from the origin to the line. This is in the direction of the line, so as we vary lambda, we will move up and down the line. If lambda was 0, we'd be at the point A. If lambda was 1, we would be here at the point 4, 4. If lambda was 2, we would be up here at the point 6, 5. If lambda was minus 1, I'd be down here at the point 0, 2. Lambda's a half, sorry, minus a half, lambda's 5, lambda's minus 3. See what's happening? And that's essentially the concept. So this is called the Cartesian equation of the line, because that's y equals a half x plus c. It's an equation involving just y and x. This is referred to as the vector equation of the line. And essentially, rather than having one equation and 2 unknowns, we've got 2 equations in 3 unknowns. So we can look at the x direction as being x equals 2 plus 2 lambda, and the y direction as being y equals 3 plus lambda as my 2 equations. So essentially what this is x equals 2 plus 2 lambda and y is equal to 3 plus lambda. Now what I could do is rearrange or solve those simultaneously to eliminate lambda, and I'll end up with this back out again. Okay, so let's just make lambda the subject of the bottom one and sub it in. So that'll be x equals 2 plus 2 into y minus 3. Divide it all by 2. I'll get a half x equals 1 plus y minus 3. And then make y the subject. I'll get y equals a half x plus 2. Nice and straightforward. Of course, because this vector here, the vector A, can be any point on the line, and the vector B is any direction of the line, then there are actually an infinite number of equations that can represent this line. So we could also have xy is equal to 0, 2 plus lambda times 1 half. Okay? That's on the line. Well, that's the equation of the line. Or we could have xy equals, let's go with minus 10 minus 3 plus lambda times minus 100 minus 50. Okay? That's also a vector equation of the same line, because this point is a point on the line, and this is the same direction as this vector, and this vector, and so on.